So what I recommend is, and it's going to seem like I'm going through the notes or the screens very quickly, I'm doing this just to condense the size of the video so it's not too long. I'm certainly not going to give you enough time to write everything down as I flip through the screens quickly. But what I want you to do is just pause the screen, or pause the video I should say, so you can jot down the notes on the screen. And if you look also on the teacher webpage, you'll see the PDF file for the notes themselves. So download that first, then watch these videos. Make sure you pause at the beginning of each slide. If I'm going to explain anything, I'll do it right away. After that, pause it, and then go ahead and write down the notes, and then unpause and move on to the next one. Alright, so this chapter obviously is acids, bases, and pH. Here's some examples of how it impacts your life, things that you've already seen or know about. When we look at acids, we're going to determine whether or not it has a sour taste. If it does, then it's an acid. Now obviously you don't want to taste anything in the lab, but I'm sure you've all had lemon juice, maybe some orange juice that wasn't super sweet, or oranges that weren't sweet, vinegar, and so forth. So it's kind of got a sour taste. Electrolyte, it conducts electricity. They react with metals and produce hydrogen gas. Remember, we did this a few times in the lab, and we put a little piece of magnesium. One time we even put zinc in there. We added some hydrogen or hydrochloric acid, and then we collected the gas and put a lit splint into it, and we saw the flame end up producing this pop sound. The formula typically starts with H. These guys are pretty easy to identify because it's got an H to start with. If you take a look at the examples over here, we've got HCl, HNO3. So these are some of the polyatomics that you know of already. These are some negative anions that you are familiar with, and we throw an H on the beginning, and now all of a sudden it's an acid. Also, it ends in ic, acid, so that kind of gives it away. If you look at this picture, you'll see the white hydrogen bonded to each one of these molecules, or in this case ions. So we've got H over here, we've got the H2, one there, the rest of this is sulfate. Over here we have the acetate, and then we have one extra hydrogen on there, and so forth. Down bottom left, here's nitrate. You should be familiar with NO3 with a -1 charge, and here's our little H, and so forth. So acids always have these extra H's bonded on there. And when you put them in solution, the H comes off most of the time, and that's what gives it the acidic nature. Bases, they taste bitter. Obviously, we don't want to taste anything in the lab. They feel slippery. If you remember doing the tie-dye, when we took those shirts out of the solution that they were soaking in initially, or maybe at the end when you rinsed your shirt off, took the elastic bands off right before you washed it, they felt kind of slippery or slimy. That's because it was in a base. They also conduct electricity. They're very caustic, causes burns. Now, some of these bases, the easy ones to identify, are the ones with the OH at the end of the formula. Not all of them have that OH. Some of them do, and that makes it super easy to identify. So if you look at the examples down here in the bottom left, sodium hydroxide, potassium hydroxide, calcium hydroxide. We looked at hydroxide earlier in the year when you're looking at your polyatomics, so we knew that this makes a +1 charge, this makes a -1, and we shouldn't have any subscripts there. But down here, calcium makes a +2, hydroxide makes a -1, so we crisscross them, and that's where this 2 ends up down here. So you should be able to write these formulas by now, and certainly you should be able to name them. Now, we looked at hydroxide, and you had to memorize that was OH with a -1 charge, but I never indicated to you, because there was no need to at the time, that meant that it was going to be a base if it had hydroxide in there. Now, I said some, I put capital letters, some. Not all of them. For instance, ammonia, you look at this formula and you say, well, where's the OH? How is that classified as a base? It is, just trust me, you'll see in a few slides why that is a base. Alright, so we have different ways to define acids and bases. There's lots of different definitions. There are different debates that occurred. Somebody came up with a definition, somebody else challenged it and said it wasn't as comprehensive as it should be. So we've got these different ways to look at acids and bases. Now the simplest one is the first one that we're going to cover. We're only going to cover the Arrhenius and the Bronsted-Lowry, but the first one is basically just look at the formula and see if there's an H. So we look at HCl. is there, or actually I should stress H in front. If there's an H that's going to separate into an H plus ion, then it's an acid. Okay? So it's got to be an H out front, and it'll separate into an H plus and then whatever your anion is. That means it's an acid. If you put it in solution and it separates and makes an OH, the OH is at the end of the formula. For instance, these two separate and you've got Na and then OH, that means it's a base. So you're looking for the H in the beginning, an acid, the OH at the end, that's a base. So we look at these two solutions. The one on the left, we're dropping in the HCl. We see that it separates into a bunch of H's. That means it's an acid. Over here, we drop in the NaOH, separates in a bunch of OHs. We see that that's a base. According to this first very, very simple, very basic, no pun intended, definition. Arrhenius, they're actually nicknamed erroneous because they don't necessarily consider all exceptions. For instance, I mentioned NH3 earlier, and I said, well, it's a base even though it doesn't have the OH in the formula itself. Now, under Arrhenius's definition, it would not be considered a base because there is no OH, but it actually is because it indirectly produces these OH ions. So we have another definition, Bronsted-Lowry, and these kind of look at acids and bases slightly different. They're looking at whether or not things donate hydrogen or they accept hydrogens. So we look at the definition here. It says HCl, which you kind of know already is an acid. Not all of them will be as simple as this. But the HCl is going to donate the H, so it's the acid. It's going to lose its H, so we consider that an acid by definition. Anything that donates is an acid. And anything that accepts the H's is considered a base by definition. In this case, this NH3, we said it doesn't really have the OH. It doesn't have that. But yet it's still considered a base because it accepts a hydrogen. Oops. Because it accepts the hydrogen, so that's the base. Now let's look at this formula. Here's HCl. Now we see that it's got an H, but so does over here. So does the NH3. There's H's over there. So let's take it a step further. Let's look at this HCl, and then let's see what it becomes way over here. It becomes just a Cl with a -1 charge. Went over here to the NH3, which is your base, so it's going to accept the extra H. So that H over here is going to end up bonding right there. And you see we end up with N and then 4 H's. So this accepted, when it was over here, it accepted that extra H. And that, by definition, is a base. So we're looking for acids are going to be donating, bases accept. Now if you look again here, we have the same exact formula, so obviously this is our acid. The H is going to come off. If we look at what happens in the long run, little Cl's all by itself. So the H comes off and it goes right up here. This formula, this should look familiar. Can you identify this as water? Here's H2O. But we add an extra H in there, and now suddenly we get this. We get H3O, and this is a polyatomic ion that I did not make you memorize earlier this year, but you should know it now. This is called a hydronium ion, and it's got a +1 charge. So in this case, your acid loses, your base accepts, your water is accepting that extra H. So in this case, the water is considered the base of the formula, or of the equation.